Hi, as Professor Goodman just said, I'm Andrea Huey, and the focus of my project was designing a low-cost ultrasound pulsar. And we'll soon see how the high voltage is coming. So before we can really get into the actual project, we kind of have to talk about ultrasound. So most of you probably know ultrasound is like how you see your baby. That's actually an array of ultrasound transducers. The device that I worked on is meant to only drive a singular ultrasound transducer. So up in this image right here is a device that Professor Guna has, and it's a pretty high functioning device. It allows for very precise imaging, but it's also very expensive, and you can see it has all these little knobs and wiggles and different things that you can do with it. But sometimes you just need the image. You don't necessarily need all of those different adjustments. They're just nice to have. So the low-cost alternative, also ultrasound works by sending out a sound pulse, and then you receive the sound pulse, and then if there's something in the way, it would reflect that. I also forgot to explain that the first time I gave the presentation, so you guys get the better version. So then the low-cost alternative is that to kind of have that same basic ability to get the image, but maybe there might not be as much adjustability, but this device is about $2,000, and my device would be built with SRD funding, so that's under $400. So that's clearly a lot better, as long as you don't mind sacrificing a little bit of that precision. So the overall goal really was to produce that same basic functionality to be able to get an image at all. So basically the device would drive a signal through the whole device that would eventually drive an ultrasound transducer. So that final output signal, the pulse width had to be less than 100 nanoseconds, which is pretty short. And then the higher function goal was to be able to make it a variable pulse width that would go between 20 nanoseconds and 100 nanoseconds. And then achieve full pulse depth just means achieve that full high voltage. So the final output pulse was driven by 150 volts. So basically it meant that we had to be able to get a negative pulse that was 150 volts. Yeah, that's a lot of voltage. And then the next goal was pulse repetition frequency, and that's just how often the pulsar is continually pulsing. So again, a base goal just to have it function was 1 kilohertz, and then a higher goal was to be able to make it variable from 1 kilohertz to 20 kilohertz, and another goal was to be able to make it be triggered externally, so you could just like push a button and then trigger. And then we actually didn't get to it because of time constraints, but another goal was to be able to design a receiver so that not only would the device send out the ultrasound pulse, it would also be able to receive the pulse and so you could actually kind of start the image. And that would have involved amplifying the received signal, because even though you're sending out this 150 volt pulse, you get a really tiny like millivolt scale pulse. And you would also need protection circuitry because the out and the in would be going through the same thing. So you don't want your 150 volt to blow out your little millivolt pulse circuit. So the general device that I did, the general block diagram, we started at an internal oscillator, and then we moved into a low voltage pulse generator, and then a level shifter, a current booster, and then there was a power MOSFET, which leads to the final ultrasound transducer. This will all make sense as we go through it. We're actually going to work backwards because it decreases in importance as we go backwards. I mean, like, they're all important, but the main part of the project was this high-powered MOSFET. The MOSFET, basically, I was using it as a switch, so it had a very high drain source voltage. This is the MOSFET here. So the drain source had a 200 volt max, and I was using 150, so ideally, no problems, and it had a very fast turn-on time of 4 nanoseconds, and that would help to achieve the really fast the pulse width that we were going for. So the drain voltage is the final circuit output, so that it's here-ish. So then we charged it. So then we couldn't actually connect it directly to the capacitor because that would require a power supply that could supply 3 amps, and you can't really get high voltage power supplies that supply that much current for under $400. So what we did instead was we took this high voltage power supply and we charged up a capacitor, and the capacitor has the ability, I think It was a 100 nanofarad capacitor, and all of the specs were way higher than what it would need to be done for this simple application. So when the MOSFET is off, the voltage here is 0, and the capacitor is charging through this 3 kilo ohm resistor. So then the capacitor is holding on to 100 volts, nope, 150 volts. And then when the signal is on here, so then when that turns on, all of the current would rush really quickly through here to ground, and then so here would be negative 150 volts. And then it would turn off pretty much just as quickly. So then, the stage right before it is the current booster stage, and that's to make sure that this right here actually sees enough current. So the current booster was 2 push-pull stages of the MOSFET switches in parallel, and that would double the current output. So that second stage right here, these are doubled, and then these are just inverting stages. The big power MOSFET from the previous slide needs 180 milliamps of current to quickly turn on. And then the stage in orange is the level shifter. So the circuit originally starts with a 5-volt signal, but we need a 15-volt signal to turn on the high power MOSFET. So therefore, we need to shift the voltage from 5 here to 15 here. And then because we're using the MOSFET, it also inverted the signal. So that's why there's so many different inverter stages, because we have to get it back to a positive input for the high power MOSFET. So then the low voltage pulse generator was implemented with digital logic, so that just means NAND gates, basically. So I attempted to take advantage of the inherent propagation delay in digital logic in order to trigger a very fast pulse. But it turns out that the propagation delay wasn't as high as we thought it would be, so there wasn't actually any overlap in the on and off times if this resistor wasn't here and if these were just connected directly. So it would just, you wouldn't actually end up getting an output here. So I added the resistor, and then that resistor meant that the signal here got slowed down just enough that there was an overlap, so that you would actually see a little spike, because otherwise you wouldn't have that spike. And that spike is basically what would eventually, going through the circuit, become that final output. And then, so how are we even going to start getting a signal in the beginning? And so that would be with the internal oscillator, and that we desire just a simple 1 kilohertz square wave. So this here, this would be triggered off the rising edge of the 1 kilohertz square wave. So there were 3 different options that we thought about. So we thought about using the 555 timer, and that would be pretty easy because it comes as an integrated circuit, so I wouldn't have had to do quite so much with designing it. It's a little bit more difficult to pick the correct component values. I did all the calculations, and I put in those component values in my prototype, and then I ended up getting like this 700 hertz repetition, so it wasn't matching the math. So then I moved to a logic gate oscillator, and you can see the schematic of that right there. And the component values were easier to determine, and I actually was able to get pretty close. I think I got like 980 hertz with the values that I had calculated for 1,000. So the math actually worked on that one for whatever reason. And then the third option was to start with a high clock and divide down, but we didn't actually end up pursuing that any further due to time constraints. So then there were a few component choices that were really critical to the project's overall functioning, and that was the high voltage power supply, because without high voltage there wouldn't have been a project, basically. We also needed the power MOSFET because we needed something that would be able to turn on and off pretty quickly, be able to handle that high voltage. The internal oscillation method that we just discussed on the previous slide was also important because that's how you're going to get a signal to begin with. And the device housing was important just because there are such high voltages, and you don't want to accidentally touch something and then shock yourself while the device is in use. So Professor Goma wanted the whole device to be self-contained. You just have to plug in a power cord and then that would be it. So that meant that I had to get the 120 volt wall line down to the 3 different voltage levels that I needed. So my high voltage power supply, I just had to connect the hot and neutral from the wall line to the power supply, and then it kind of handled the rest, and it would output a stable 150 volts DC. And then I need the 15 volts to power all of the MOSFETs, so like all of that stuff. And so I had to find a transformer, and that was an 8.6 to 1 transformer, and that I used to step down the 120 volts AC from the wall to 14 volts AC. And then I designed a rectifier circuit that would take that voltage and make it like a flat DC. And then the output of that was tied to a voltage regulator design that I had calculated component values for to get to 15 volts. So that was how I was able to get a flat 15 volt DC. And then 5 volts was needed for these 2 digital logic chips. And I just took the 15 volt output and tied it to the 5 volt. And then I had another voltage regulator that was designed for 5 volts, so 15 was just tied to 5. So then initially, some results of just the raw circuit outputs for the overall device. Over there, this is the input to the high power MOSFET. And so it's not actually reaching 15 because that's up here, but it was enough to trigger the MOSFET to turn on, which is all that Professor Miller really wanted, just to make sure that it could turn on the thing to produce the high voltage spike. And then this is the raw output, so that's the output measured after the capacitor. And it's at minus 140 because the data wasn't cooperating when I was trying to save it, but I did get it down to 150. So. And then we connected my circuit to an ultrasound transducer, and we were able to measure that using the original industry device that I was trying to replicate. So we sent a pulse through water to that receiver, and then we measured the received pulse using a digitizer connected to MATLAB. So this is the received pulse count. So then this is the part that we care about. And on the next slide, we see that so the industry device had a couple different energy level settings. So mine is here, and this was mine, and that's about negative 0.06 to 0.06. And then this was energy setting 2, and it's just a little bit under negative 0.05 to 0.04. And then this one was about negative 0.125 to 0.75. So basically, my device was able to produce a final waveform that fell in between settings 2 and 3. So that was pretty neat. My device didn't have the ability to adjust the magnitude of that pulse. And then, so this is what the overall thing looked like. It's a pretty big box, but it gives you a lot of room for maneuverability. So then, these are all of the components put together. That's the VNC output, and there was a power switch, and it's on in that slide. So kind of just to revisit some of the original goals, we were able to get a pulse width of less than 100 nanoseconds. The pulse depth did reach the negative 150 volts that was so important. We also got the oscillation frequency of 1 kilohertz, but due to time constraints, I wasn't able to get to the adjustable frequency or the adjustable pulse width or the external trigger. And I already talked about how the receiver was scrapped pretty early in the project due to concerns about time. But the main kind of idea was low cost, and I paid for the whole thing with SRG money, so that was fine. And I did have a few ideas about how to achieve some of those goals that weren't actually met. So in order to get a variable pulse width, I could change the delay resistor from this slide. So different values of that resistor would actually produce a different final pulse width, and that was something that I had observed experimentally. I just hadn't done math or done any calculations to find, like, oh, if I use this resistor, that'll correlate with this specific pulse width. And then variable frequency would be to change the timing resistor, and that would be the resistor that I used on the on the internal oscillator circuit. And again, I haven't done specific calculations, but if you change the value of that, there's one resistor that controls the oscillation, and if you change that value, you could change the oscillation. To include an external trigger, you'd have to include a method of bypassing the internal oscillator to trigger it off like an external oscillator, or you would just have to have a way to turn that off or on so that you could just press a button and tell the device to start oscillating. And then receiver circuitry, we talked about it at the beginning, but again, the return signal would be on the scale of millivolts, so you have to filter out a lot of noise but retain signal data, and that's kind of hard to do on the millivolt scale. And the receive is routed through the same output, through the same cable as the output, so you have to make sure that you're protecting your very delicate receive circuitry. Yeah, that's it.